Hello everyone, my name is Abeer Alamoudi. I'm a first-year PhD student at King Abdullah University of Science and Technology. I work in the Communication and Computing Systems Lab, and on behalf of Dr. Abdelkader Chilik and Professor Ahmed Al-Tawil, I'll be presenting our paper, Energy Efficient Capacitive Body Channel Access Schemes for Internet of Bodies, presented at the IEEE GLOBECOM' 2021 conference. In our presentation, we will have a brief overview on the IUB and the various communication alternatives to implement it. How can we regulate the communication between multiple nodes through access schemes? And then we will formulate our problem, present our solution with regards to power allocation. To complement the previous discussion, we will present numerical simulations, and then we will conclude our presentation with some final remarks. Despite the maturity of the existing healthcare systems, in the near future, they will fail to address and accommodate everyone. This is due to the ever-growing human population, pressuring the current health resources. This necessitates the need for a scalable, cost-effective, smart healthcare systems. Not to mention the recent global health crisis, COVID-19, which caused a depletion in resources, situating many healthcare centers on the brink of collapse. This stressed the need for transforming the infrastructure even more. As a proactive support for future healthcare systems, the Internet of Bodies is then introduced. The Internet of Bodies is a network formed by wearable, injectable, ingestible, implantable smart objects that can give an insight about the overall health of individuals in response to daily activities. And this information can be further communicated with health professionals if needed. Owed to the various IUB nodes that can be implemented, then IUB can transform our perception of various sectors and applications, including personalized medicine, remote patient monitoring, self-care, and safety of critical personnel. Having a root in wireless body area networks, then the IUB can capitalize on the IEEE 802.15.06 communication standard, which defines three communication physical layers: narrowband and ultra-wideband RF communications, human body communication or body channel communication. The IUB systems, in fact, can be readily implemented using pre-existing RF technologies. However, due to their highly radiative nature, they cause a reduction in energy efficiency as they emit energy in unneeded directions. Moreover, the interference problem, which will become more significant when operating in highly demanded license-free bands. Coming back to the radiative nature, which imposes security threats on the sensitive data. As an alternative, the body channel communication, which is also defined by the same standard, which confines the transmission signal to the human body via electrostatic fields at 100 kilohertz and 100 megahertz. And thanks to the body conductivity, the signal then experiences a lower path loss, which is translated into a lower transmission power. In addition, it improves the signal confinement, reduces signal leakage, and as a result, it enhances the physical layer security. To further compare between BCC and RF, we look at existing BCC transceivers and RF chips. We see that BCC transceivers highlighted in red can operate at an efficiency in the order of picojoule per bit, while achieving high data rates in comparison to RF chips. This is a very promising energy efficient technology to implement IOB. However, most of the research effort is focused on optimizing the transceiver design and channel modeling, yet networking and communication requires further investigation. Therefore, in this work, we look into orthogonal and non-orthogonal multiple access schemes to permit multi-point communication, and we present optimal power allocations for both schemes, uplink and downlink traffics. We address the merits of the proposed schemes through simulations. In our system, we will consider having a wearable hub device. In this case, it is the smartwatch, communicating with K on-body source nodes through time-slotted uplink and downlink transmission. This hub device is also capable of communicating with off-body entities but through RF communication. Let us focus on the on-body communication. To regulate the communication between multiple nodes sharing the same medium, we will first look into the orthogonal multiple access schemes. In this scheme, Each node is permitted to communicate with the hub over a dedicated link to mitigate the multiple access interference. This link is an equal portion of the bandwidth. In the uplink direction, the hub will then receive the weighted transmitted signal through the pre-assigned link, and this signal has a signal-to-noise ratio that is function of the equally divided bandwidth, as we see here highlighted in orange. In the downlink, the hub will use the same dedicated links to communicate with the nodes of interest, utilizing its own power budget for the transmission. Hence, the hub will divide the power equally between the node as a result, and the SNR will be in the following form. Another scheme to regulate communication is the non-orthogonal multiple access scheme, NOMA, where all the nodes can communicate over the entire bandwidth and the entire time slot concurrently. Hence, the hub receives a weighted sum of the transmitted signal, all having weights between 0 and 1. And to retrieve each signal, the hub is required to perform successive interference cancellation, SIC. And for the success of this operation, the hub is required to receive distinctive power levels. Then the decoding follows the following order, where the hub decodes the observations of higher rank nodes, and lower rank nodes observation will be regarded as interference. As a result, the signal to interference plus noise ratio, SINR, is defined as follows, where the first term in the denominator constitutes the interference coming from lower rank nodes, and the second term constitutes the SIC imperfections induced by hardware limitations and channel estimation errors. This is modeled by epsilon, which has a value between 0 and 1. For the downlink, the hub transmits a superimposed weighted sum subject to the maximum power transmission. That is, the sum of power weight should be less than or equal to 1. In this direction, each source node is expected to perform SIC, and the decoding order is reversed. Hence, lower rank nodes will be decoded, and upper rank nodes will be regarded as interference. Moving on, the main objective is to have long-standing networks that are capable of meeting the various quality of service demands, QoS demands. And for that, we look into the power consumption in uplink and downlink, where the power consumption is contingent on two parts: the circuit power, which is a function of the energy efficiency of the transceiver itself, and the transmission power. And since we are focusing on the networking, then we aim to minimize the transmission power. Accordingly, we formulated the problem for uplink and downlink to minimize the transmission power consumption subject to QoS constraint in both traffics and the maximum power constraint for the downlink traffic. Now, these problems can be easily and readily solved put into convex optimization solvers. However, for the aim of hardware complexity reduction, a closed form is then more desirable. The closed form solution as a function of the SINR thresholds and epsilon can be obtained solving this equation based on the Perron-Fabinus theorem, where P star is the optimal power vector with entries function of the channel gain and the power weight. We derive this for OMA uplink downlink and NOMA uplink and downlink. To verify the CF solutions, we compare the results with results obtained by CVX, a convex optimization solver. And for both methods, we plotted the sum of power weights with respect to QoS and K, the number of nodes. We see that both methods are tightly matched, verifying CF results, as both results demonstrated high power sums at high QoS demands and larger network size. Another important metric is the fairness in power allocation for both methods. So we exploited the Jane's fairness index, and we plotted this with respect to SIC and channel length ratio. The channel length ratio is modeled as the ratio of the channel lengths of the furthest away node to the hub and the closest node to the hub, fixing the closest node to the hub at 10 centimeter, while sweeping the other node from 30 to 180 centimeters. We found that CF results outperform CVX. Indeed, at low SIC values, both are highly influenced by the channel length ratio, reducing the fairness at high ratios. Interestingly, both methods achieve high fairness at high SIC because in this case, all the nodes will be transmitting at maximum power and there will be no power control in this situation. However, this is not an energy efficient network. To extend the network lifetime, we considered a duty cycle transmission as we denoted the duty cycle by alpha K, and we defined our network lifetime as the lifespan between network initialization and the first battery depletion in the network. And we plotted this for various QS demands and various alpha values. We can see that operating at low QS and alpha improves the network lifetime, but most importantly, we touch again on the importance of having an energy efficient transceiver. For example, the BCC transceivers in picojoule per bit compared to RF chips in the nanojoule per bit. Another important analysis that we have looked into is the maximum feasible number of nodes to design the network without violating power control nor QS constraint. In our derivations, we noted that the NOMA network size will be contingent on the location of the highest channel gain node, while OMA is dependent on the lowest channel gain node. Accordingly, we assign two locations for the highest channel gain node, 20 and 100 centimeters, while fixing the lowest channel gain node at 180 centimeters. We then plotted Kmax closed form and simulation results for both NOMA and OMA with respect to QS demands for both uplink and downlink. We found that the result justified our derivations, putting a condition on designing the NOMA network by optimizing the location of the highest channel gain node to admit more users in the network. However, regardless of the two cases, NOMA scheme still outperforms OMA. And as we can see that the difference between OMA and NOMA at 100 centimeters in the downlink is larger compared to the uplink. This is because in downlink OMA, the Kmax is limited by the bandwidth and power budget of the hub. We also investigated this with respect to transmission power, once again pronouncing the superiority of NOMA over OMA by allocating more nodes even at very low transmission powers. And as we increase the maximum transmission power for the uplink traffic, we see that we are closing the gap between OMA and NOMA at 100 centimeters. However, this is not the case for the downlink because, again, in the downlink, the bandwidth and the hub power budget limit Kmax in this situation. In conclusion, this work is a step forward towards perceiving BCC from networking perspectives to adopt it in IOB systems. The power constraint and form factors still obstruct the long-standing networks. We have looked into the ultra-low power OMA and NOMA schemes, and through simulations, we verified that NOMA schemes enhances the network size compared to OMA, introducing a trade-off in complexity and performance. We finally would like to thank you for your time and for listening to our presentation. Thank you.